When you're dealing with high-pressure piping, the miles of thick, hardened steel aren't usually what keep you up at night. The true test of your system's reliability almost always comes down to the smallest components, the joints. A mechanical breach in an industrial line triggers immediate pressure loss, hazardous material spills, and forced plant shutdowns. That brings us to the core engineering dilemma of connecting any two pipes. You have to choose between locking them together permanently to handle maximum stress or building in a way to easily open the line for future maintenance. To navigate this trade-off, we are going to look closely at three specific connectors: couplings, unions, and nipples. Selecting a fitting involves matching the physical shape to specific pressure classes, volatile chemical environments, and the realities of a long-term maintenance schedule. Balancing the need for permanence against the need for accessibility is the defining difference between building a resilient system and actively engineering a future leak. Let's start with the coupling. This is the primary choice for a permanent line extension. Whether it's a full or half coupling, threaded or socket welded, it joins two pipes by creating a continuous, streamlined cylinder. That low-profile design maximizes the joint's structural integrity. The major trade-off here is total permanence. Once a coupling is fully installed, especially if it's welded, you cannot take that joint apart. Disassembly requires physically cutting the pipe. You use couplings for long horizontal runs of water or gas lines across a facility, areas where you never expect to open the system back up. If you do need to get back into the system, you use a union. Think of this fitting as your maintenance gateway. A union uses a three-part design: a male end, a female end, and a tightening nut. This allows a technician to easily decouple and reconnect the pipe later using nothing but a wrench. However, that modularity comes at a cost. A union is bulkier and introduces multiple potential leak points where those three pieces meet. Because of this, they are generally restricted to lower pressure, small bore systems. You'll find unions placed immediately adjacent to pumps, chillers, or filters, components that have to be routinely pulled offline and replaced. Finally, we have the nipple. This is essentially a structural gap filler, a short length of pipe with male threads on both ends, used to connect two female fittings over very short distances. You have to be incredibly careful with close nipples. Because they are threaded end-to-end with zero bare pipe in the middle, there is nowhere to grip them with a wrench. Extracting a close nipple later often means destroying the threads entirely. Picking between a coupling, union, or nipple is a direct commitment to exactly how you plan to maintain that specific foot of pipe for the next 20 years. But the physical shape of the fitting won't matter if it can't withstand the internal system stress. This chart shows the specific pressure capacities of forged fangs, mapping a Class 2000 threaded fitting against a Class 6000 socket weld fitting, along with their required pipe schedules. Specifying a Class 6000 socket weld fitting guarantees structural safety under extreme, high-vibration industrial pressures. But that durability demands much thicker Schedule 160 pipe to match. It also requires specialized welding labor, rigorous weld inspections, and massive material costs. On the other end of the spectrum, Class 2000 threaded fittings bypass those hurdles. They are highly efficient and cost-effective for standard, low-pressure fluid transport. Over-engineering your pressure class burns through your project budget, while under-engineering invites immediate structural failure the second the system comes online. Even a Class 6000 pressure rating is useless if you pump the wrong fluid through the line. If the material dissolves from the inside out, the joint will fail regardless of its thickness. This chemical resistance scorecard maps standard PVC and CPVC against exotic plastics like PVDF across three specific chemical groups: aliphatic solvents, strong acids, and esters. Look at the PVDF column. It earns an excellent rating for resisting strong acids, halogens, and aliphatic solvents. If you are operating a severe chemical environment, that resistance easily justifies its premium cost. PVC, on the other hand, is perfectly sufficient for weak acids and salts, but if it is exposed to aromatic solvents, it suffers a complete failure rate. Once you have the right fitting, the right pressure class, and the right material, the final step is actually installing it. specifically sealing the threads to prevent fugitive emissions. A reliable seal isn't a guessing game. It requires applying an anaerobic pipe thread sealant to the male end and tightening the joint to guarantee 5 to 6 full threads of mechanical engagement. That premium sealing method requires perfectly clean threads, precise torque tools to avoid over-tightening, and a full 24-hour cure time before safely pressurizing the line. It is much slower than a quick wrap of Teflon tape and pipe dope. When a joint leaks, it is rarely a defect in how the fitting was manufactured. It is almost always a failure of the material specification or the installation technique. This decision tree shows how to navigate all these variables, starting with the ultimate determining question: is frequent maintenance required at this specific joint? If the answer is no, you go down the install and forget path. For miles of uninterrupted oil, gas, or chemical pipelines, you specify socket weld couplings to maximize permanent structural strength. If the answer is yes, you take the dynamic maintenance path. For chillers, HVAC units, or chemical feed pumps that need annual replacement, you specify unions and nipples to create modular, easily removable zones. Then you layer the pressure and chemistry choices onto those paths. You allocate Class 3000 or exotic plastics like PVDF to the hazardous, high-pressure nodes, and use Class 2000 or standard PVC for the low-pressure nodes. Successfully joining a pipe demands technical alignment well beyond simply matching the inner diameter. True system engineering means matching the fitting's exact pressure class to the physical load, the material composition to the chemical fluid, and the connection type to the facility's maintenance schedule. Ultimately, mastering the strategic trade-off between permanence and accessibility defines the long-term survival of the entire industrial infrastructure.